All right, welcome. Today is February 17, 2021. This is TRiRODS first of 2021. And we've got Dan Moore from the iRODS Consortium. He's going to talk about the work he's been doing with the Python iRODS client, some things that are already in there, and then some things that are coming very shortly. Take it away, Dan.
Yeah, thanks, Terrell, and greetings and good afternoon and good evening to everyone in attendance. I want to address today a couple of basically capability upgrades in that are new and upcoming in iRODS itself, and that can now be or will soon be, depending on the case, accessible within the Python iRODS client library by client applications using this module. Which is a pure Python module lets you interface as a client to iRODS. So the first of these two is already available as of the last release of iRODS and PRC. The client library is abbreviated PRC. So atomic metadata is that first one that is available, and parallel transfer is the second. It's not really available until 4.2.9 technically. It is actually a new take on an old way that we've had in iRODS for a long time of getting data to and fro between a client application and the iRODS server. So with that, we'll look first at atomic metadata. What is this actually? It's metadata operations have, of course, existed for a long time in iRODS. What you're doing there is you're adding, removing, manipulating, replacing in a set operation, replacing, if you like, AVUs, metadata AVUs, which are essentially triples, attribute value unit triples that exist on a catalog entity in iRODS. So the new aspect of this atomic metadata is the atomic part, of course, that lets you do a whole batch. I've tried as many as tens of thousands. So it's good to know it's robust enough to handle very, largest numbers of these, largest batches of these at once. And so the idea is that you can do it atomically, and that is all in one database transaction. This, of course, also gives you increased efficiency. And the numbers I've seen in some very short trials is that you get one magnitude at least over the case, which would have been the old case of doing each of those AVU operations in its own single trip to the catalog and the database. So, and as I've stated, this is already available as of 4.2.8 of iRODS and the recent release of the PRC. We've implemented this atomic metadata in the server as a response really to some member and general iRODS community requests for this. One of the main applications, and the original probably, was Utrecht University developed a web application which needed to use metadata templates, a sort of schema for validating that you have essentially a valid set of metadata on an object. And it's best to do things atomically. All in one transaction is either going to succeed or fail if you're going to do that sort of thing. Also, another use case is you may see an ingest situation where a client deals with an incoming set of images, say from microscope or satellite, potentially, and these may have large amounts of metadata that can be extracted from the header during the process of ingest into iRODS and then attached as AVUs. You'd like to be able to do that fairly efficiently, and this atomic metadata ends up being pretty good for that. increasing the efficiency of adding those AVUs onto the object. And here we have a concrete example of the interface to this capability from within the Python RODS client. You can import the iRODS meta object as usual, which represents an AVU, which, you know, we've long been able to do this within PRC again, but now we can set a bunch of these operations within the same apply atomic operations call, and it's all done as one transaction. So that's, you know, the top example is that general use case, and the bottom one shows that you actually don't have to you know, submit to, oh, it's all, we've got to, you know, we've got to build it all into the same call. We can actually build a list of these operations programmatically, and I have to accentuate too that this is an ordered set of operations. So when you do remove and an add, for example, of the same exact identical AVU, which you're doing, well, actually, under conditions, if the tag and value are the same, but the units are different, you could be doing a set by doing a remove and add, but the same wouldn't be true if you were doing the add first and the remove, of course. So it is sensitive to order of operations, the set of operations you feed to this call. So in the one below, you see that we are actually building a list of operations which will remove all of the metadata items on an entity, on an iRODS object. And basically at the same time as we're removing all of those, we're also adding a flag that happens to bear also the information of what PID the running process is. This is, you know, a semi-practical example, but, and then you see that when you are programmatically building this list as a list called operations, you can use the starred notation in line 6 at the bottom. The lips are getting very dry for some reason. Okay. So right now we'll have an even more concrete demonstration. I'm right now connected to a network here at home. I have my local client. I actually can fire off a script, a demo, and I actually did have to reboot before this session, so I have to bring up my commands that are to be typed or cut and pasted. Okay. All right, so we have a virtual environment with Python 3. I've actually installed the Python RODS client library into that virtual environment, and we can use this demo script. First, I will believe the object is already there in AVU test. I'll actually set a few AVUs on this object. Or not. I didn't set the object name, I'm sorry. Huh. So I'm setting and I'm using the old way through iCommands to set 4 different AVUs on this object, data object. So you see them right there. They all have the same attribute and value, just different units fields, 0, 1, 2, and 3. And I'm going to show using this script. And basically what the script does is get a session, take some arguments from its command line, which is the data object path, and the metadata name, value, and units. And the idea is we're going to replace all of the listed AVUs with a single one that's named on the command line. We basically collect all the matching AVUs that exist that match by name and value to what's given on the command line, and then we use the units that are given on the command line to replace all of those with a single AVU with the new units. So to make it clear, let's list those again. Okay, we've done that. And now we see all 4 of those have been replaced by a single one in a single transaction, and the new units are being used to replace the old units values that existed before. So in effect, we've done a set, really, a set of an AVU that will, and this is how it would have been called in the old way of setting, the old API with setting metadata. You would have called this a set, and it would have replaced all the existing AVUs by that attribute and value tag. So do we have any questions so far? Is anyone there?
So you said you tested this with tens of thousands of entries?
I did, in fact. I did a shorter test in which it seemed to be taking about 10 times as long to do them individually as it did in the atomic operation.
Well,
And then I did a long.
Right.
That was, sorry.
I said that sounds about right. That's a lot of round trips.
That's right, and that, I think that was about 100, and and then I tried it with tens of thousands. It was probably like 70,000. I think it took a few minutes with the atomic.
That was my next question. So it took a few minutes. That's still not bad for 70,000 AVUs.
No, I know for a fact it's going to take much longer. You'll be sitting there for an hour, probably.
Easily, yeah.
Yeah. And okay, if there are no more questions.
What does the failure mode look like? So if something goes wrong, what kind of error do we expect back?
Right. I only expect the only failure mode I expect right now to happen is really in some sort of network outage.
Or someone pulls a plug on the database while you're adding 70,000 AVUs.
Or the network board out of your computer. I mean,
that would do it too. I mean, does it just throw an exception then? Like what is the expected failure then?
Well, yes, I believe that would have to be, I mean, and people who have used the Python iRODS client module have probably seen this before. You'll probably just get a connection, an exception object being thrown out of the connection because you won't be getting a response. Admittedly, we're having to backfill some of the errors that actually error codes that exist in the iRODS server. I think I did this recently in response to someone in the community, but you don't know what an exception is going to look like until it happens. So a lot of those errors are represented in the PRC, but a few weren't, it turns out.
I got a question similar to what Jason asked.
Mm-hmm.
So when there is an error with the atomic metadata, operation. It should supply like some JSON information that explains which operation it failed on.
Okay.
And I guess is that reported back or?
Well, as I say, I haven't really seen the failure mode, and originally when I did implement this, I expected to, because I thought that the add and remove would elicit failures the same way they did in the old metadata interface, but they don't, in fact. So, I mean, I guess I could try to pull my network cord right now and see, but you wouldn't
Oh,
see,
okay.
you wouldn't see and hear me anymore. But the fact is that you can now, with this sort of batch or atomic metadata, you can add an ADU when it already exists, and you couldn't do that before in the old interface. And you actually do not get an error. You don't get an exception of any kind. You can also remove one which does not exist previously. And I think this is all necessary for certain use cases. I mean, there are only, correct me if I'm wrong, Corey, because you implemented this on the server side, correct? But the add and remove are now the only two operations available in the
Yes.
metadata, right? So I think that the mindset here is that an remove followed by an add can be equivalent to a set.
Yep.
Yeah. So, I mean, you would kind of expect that, I mean, remove, well, right, add, remove, I don't know. But I mean, I have definitely verified that add does not create an exception condition when that AVU already exists. And similarly, remove. So in other words, you can unconditionally of whether the AVU existed before or existed with, say, a different units field, you can unconditionally do a set. And that's because the remove doesn't actually create an error condition, whether or not the AVU existed previously. Any more questions? Okay. We'll now go on to parallel transfer. As I've said already, there was an original capability. It's been around for a long time, by which clients could put or get data as a put files, data objects into iRODS and get them back. So it has used server coordination so that what you typically get is with small data objects that you put in get, it's a single buffer transfer, and it's not at all multi-threaded and very simple. You simply do this through the client connected server. And if, however, that the size of the object being transferred in either a put or get is over a certain threshold, and that is 32 megabytes by default, what will happen is that the iRODS grid will open up a portal on the destination server that is the ultimate resource, the storage resource that is the target of the get or put. And so high ports will have to be available on that, and extra socket connections will be made external to the main connection over which the client can get or put the data object. So this capability has actually never existed within the Python RODS client. So you've never really had this multi-threaded ability at all. And so this new ability we're talking about, parallel transfer, is detailed below, and this is what's now being added. It's in a sort of developmental phase and will be ready by the release of 4.2.9, this upcoming release. In this new approach, the client will actually be more under control of the operation. It will be the agent that spawns threads, and it will actually reuse the connection data that's already available to it. So we sort of colloquially call this the multi-1247 parallel transfer. I believe that the PRC is Python client is the first client to implement this. And then there is, along with this new release of 4.29, which will happen soon, there will also be a release 0.9.0 of PRC to correspond with that, and you'll have this ability to do the new multi-1247 parallel transfer, multi-threaded. So to detail, just for historical purposes, really, the way this used to be done, you can see that the client here, it always has an immediately connected server. The client connected server is given a request in this case to get an object. So this could be an iGet, and probably is, because iGet and actually iPut, those two commands are the only clients that I know of right now that implement this, the old-fashioned parallel transfer, multi-threaded transfer. So then what happens is wherever this data object is, that request is directed there. And ultimately you will have to have high ports open for a separate sort of out of band, almost really, with respect to the primary connection. You'll have these multiple channels of transport for the data object. And that's how with iPut or iGet, with the $N option and a number specified after that, you can actually specify a number of threads. Usually 3 or 4 is and this, it's been verified that with, I believe it's with 3, it's been proven by a white paper that an organization did some years ago, that pretty much maxes out any network path, saturates it. So there's, in other words, there's really no point in going over 3 or 4 threads. So, and that is also going to be true of the new method, just incidentally. So that's the way this approach works. And there are limitations to it, obviously, which is why we're planning on going to the newer approach. It is sometimes inconvenient to keep these open, high ports open, the 20,000 through 2199. It is a somewhat complex system in which retries would be a little more difficult than perhaps they should be or could be. You don't really have much control from the client side, so you could try to interrupt the connection, for example, and you wouldn't be totally successful because the servers would still be trying to move that data. Also, if you find that you're using this the Python client or any client really to get to basically an iRODS system that's behind a firewall, the only way, the typical way that's done is to have a DMZ server outside of that firewall that you immediately connect to from the client. And it's really, in the old approach, it's neither easy nor really advantageous to keep high ports open for that, since I believe it. My colleagues can correct me here, but in my understanding of the old approach, you would only end up being able to transfer the data over this original path anyway, since these ports could not be opened from behind the firewall for the client to connect to. So typically you have to use a dash capital I believe, option to force that if you're going to an iRODS system that is mostly behind a firewall.
Yes, and the capital I was only a single threaded, so you lost all the benefit of the speed, but you might be able to get past the firewall.
Right. So this is the new approach. you as the client can actually be redirected through your connected server to the destination server, which is the target of the other end of the transfer. And really all of this can be done over that single port, 1247, nominally 1247. And this sort of moves a lot of the control to the client in that, and it makes the idea of retries a bit simpler and more easily implemented. Again, clients are in this new situation with multi-1247 are in direct control of the data movement. They spawn the threads and they put the data through or get the data through those channels opened up on the destination server. Now, the current model that I will show of the PRC doing parallel transfer does not yet do these direct connections. That is upcoming. That should be baked into the PRC and the next release of iRODS. So so also because you're doing this parallel redirection, you know, even in the case of a firewall, you can get through effectively to that destination. It may occur through the client connected server if in the case where those high ports are not, in any situation where high ports are not made available. And what we'll probably do is have this information made available through the initial conversation made by the client and the client connected server. So you'll know at the outset whether or not you're able to do these direct connections. But it certainly is advantageous in situations where you can do those because it diversifies your network paths that the object that the data can flow over. So it's a lot, you know, it will end up being as fast in most situations and more flexible in that it can extend to more situations than and maintain a parallel performance relative to the old approach. And so this has actually been tested so far in a limited fashion so that we can at least see a palpable difference between what you get from a situation with single-threaded transfer and a multi-thread transfer. So this is really a comparison between iPut and iGet using, you know, in this case, iCommands will use the old way of moving data in parallel. And what I'm showing with these results is that yes, although the method being used in the bottom row is actually the new multi-1247 way of doing it. It's still a similar situation. It's multiple threads moving the data in parallel. So you would expect comparable performance here, and that's what you get. So what you don't see is the full possibility, of course. If you were operating over a more high performance network, you would expect the latencies to be longer relative to the individual bursts of data transfer. So there'd be more gain to be made by, and that would be reflected. You might see an end time speed up for end threads, but we'll be testing this out soon on a higher performance network. So as I've said, this approach is multi-threaded. The new parallel transfer engine implementation within Python will actually switch over to a parallel put or get. It'll do so transparently, seamlessly, if you exceed the threshold of size. This way of doing things is actually going to be limited to the next release of the server. It relies upon 2 new APIs within the server. They essentially let you open replicas on an object so that when you do an end thread transfer, even though they're end threads transferring in a put operation, you don't get any more than, say, 1 invocation of a post step, for example, because you don't have n file closes. You have n minus 1 replica closes and 1 file close. So it's essentially 1 put operation. Also, we get a benefit that we don't have to reproduce encryption in a sort of out of band way, the way we have to do with the old style of parallel movement, data movement. We actually could not use the SSL credentials. We maintained the original connection, and the extra data flows over sockets had to have a separate encryption mechanism. Similarly, if we wish to implement other performance gains, such as perhaps, we're entertaining this idea of dynamic compression and recompression, perhaps using the Google, what is it called?
Snappy.
Snappy, exactly. So we could easily use the Python Snappy module to implement this on the client end and have that done once, basically implemented on the server end, which I believe Corey has made some gains in those terms along those lines. And since we are going along a single code path, we are only going through the primary connection and duplicates of that connection using the same credentials and other data, including SSL credentials. We're basically going through 1 code path all the time, and we can do all this work once, whether it has to do with encryption or compression or whatever. And that is a solid gain opportunity, definitely. So as I've said, the puts and gets at present flow through the client's directly connected iRODS server. And in the future, we will make that conversation yield some information at the start as to which hosts the client might also connect to on the same iRODS grid, if we want to sort of diversify the flows and get more performance gain. So right here, we'll show right here I have on the a remote machine. I have the iCat running 4.2.9, or as close as we've gotten. We haven't actually bumped the version number yet. It's still being called 4.2.8, but it's running over here in this window, and I'm tailing the logs on that machine on the iCat provider. And here I have a machine with the Python client only, no server running. And I'll show a couple of gets and puts in the old and the new style too. Oh, how am I doing for time? Oh, I'm at 40 minutes, aren't I?
It's fine.
Okay.
This is the last hurrah, I think, right?
Yes.
Yeah.
So I've created a 2 GB file, and we'll see how long multi-threaded output takes to place that into iRODS.
I'd like to just throw out there that, as Dan mentioned, the biggest goal here is to putting the power into the hands of the client, because the existing parallel transfer made a bunch of assumptions on both the server side and the client side, and those assumptions had to agree. And things like buffer sizes, for instance, the Python client can now just pick whatever buffer size it wants to send over the wire. So if you're in a WAN situation, you can cram as much data into that pipe as you want. And the server will just, behave the same. There's no negotiated terms on both sides of this in order to make the parallel transfer work.
I wanted to emphasize that I'm showing an IPS. So I'm using an I command to show the current connections that are active. And when I do an I put with the original way of doing parallel transfer, you only actually see one connection working, even though that is multi-threaded, I believe, within that connection. So the difference, really, one of the differences between the old and new way of operating is that we duplicate the original connection data, and you'll see that when you'll also see that the time taken is similar. So we'll do the comparable case within the new style of parallel transfer. What I've done is to tell it that we actually have a 429 server, which it won't immediately recognize right now because we're getting from the server that it still thinks it's 428 because we haven't done the server bump. But this is also convenient because we can illustrate the difference in performance between the old and between a multi-threaded and single thread transfer. So all right. Yes, we see that it's 18.4 very nearly in both cases. This is the I put with the old parallel transfer, and I've just written a simple script that calls the put basically the put method of the data object manager to get this 2G test file.
Can you show us the short put.py?
Oh, yes.
And then I don't know if anybody saw it, but there were 3 things up there in the IPS while he ran that. So you could run it again, Dan.
Yeah,
if you
yeah.
want to. While we look at the code.
Yeah, here we go. I think I deleted it twice. So I got an error message. But you can see that I've added debug messages just to make sure that I'm actually going through the parallel code path. And I am. So the next thing I'll do for comparison is to actually suppress that environment variable there so that it now thinks that it's going over to a 428 server. So I'm lying to it, really. I'm saying don't use that capability. So I'm unsetting that where it said 429, it'll assume 428 now.
And where is it getting that version?
Oh, through the connection info coming back. I believe it's the startup pack that exchanges some information, and yeah.
Yeah, you send the startup pack and then receive the version, and that's the version you're using unless you're overriding it. Very good.
Exactly, to determine whether I can do the multi-1247, whether those APIs are available to me.
Right, so this will be seamless for anyone who has existing Python code. As soon as they upgrade their server and upgrade their Python, then they will, without changing anything, theoretically get the benefits of parallel transfer instead of having to change anything.
Right, so that's a 3.5. It's predictable. It's small, but it's predictable that it's always 18 versus 20 some seconds. Yeah, we do expect to see larger performance difference when we do the full test on a high performance network.
Very good.
So yeah. Let's see. All right, so as I've stated, it probably ultimately we do want to allow the client to be able to connect directly to destination servers where possible. And that is work to be done. Also, there's the ability in the old iPut and iGet to show progress to the user. And that's another thing. On my original development to this PRC parallel transfer code, I did have a sort of a homemade progress bar, but it would probably make better sense to make an interface that other progress indicators could use. There's some nice ones out there that could show the progress on each thread, for example. Also, lastly, in some ingest scenarios where you have large files being sent into iRODS with the put append mode, for example, there may be large amounts of data being appended to already large files, and you don't want to have to re-ingest the whole thing. So it would be very good, for example, to be able to provide an offset to this put and get call to say start at this point, you know, in the file object, rather than transferring everything from the beginning unnecessarily. So that's for situations in which you know your data is always being appended to, and the original data that was already written has not been changed. And that's really all I have to present. Are there any questions?
Do you happen to know, Dan, when iPut and iGet are going to learn how to do this?
When iPut and iGet can
know how to do this also?
The
multi 1247.
Multi 1247. Are we going to do that? Yeah, I guess that we should.
Yeah, so this is basically the first client that's implemented this as a test to figure out what's hard and what's good.
Exactly.
And you know, we'll use the learnings here to decide when we you know, port the main iCommands and stuff over. You know, how that's received by the community, and scenarios where that might be surprising to people. We don't want to break their existing expectations, but we do want to make the nice things nice.
I mean, theoretically, and Python was originally made to be a pseudocode-like language. So essentially, we've written the pseudocode. We can throw this right into iPut and iGet, can't we?
Yeah, I mean, it's just connections.
Yeah.
Yeah, I mean, we already have the parallel transfer engine implemented in C++. We just,
oh, right.
Right. We just need to roll it out as an iCommand.
Yep.
Mm-hmm. Is that already in convenient, like a convenient call for like a client endpoint can be provided for?
We're waiting for 429 and the finalize API and all the stuff Alan's working on in order to hit all of the use cases that we've had slated for that bit of code.
So yes, it's in there, but it's not. 429 is a big deal.
Mm-hmm.
It's a huge deal.
Exactly. So we'll be able to roll that out with after 429 has been released. So we 4210 or 43.
Right. Very good.
There's still some optimizations left on the table that with the ring buffer. I know Jason's mentioned this before, but you know, the S3 transport has that ring buffer in there that we could, you know, add into the parallel transfer implementations for Python and C++. Yep. And hopefully we should be able to, you know, increase the gap between the traditional parallel transfer and the new one.
Yeah, absolutely. I wrote that. I just wrote that down for the Python implementation.
Right. Keep the pipe full.
That's right.
What it's about.
Very good. Well, 50 minutes in, we did it.
All right.
Anybody else have any questions?
Not really a question. I'm Paul from K11. We are using actually HA proxy in between the clients and the real iRODS primary servers. I'm just wondering what we might need to cope with if we want to use or continue to use HA proxy or another TCP proxy in between to handle all this. But maybe at first sight there is actually not much required for changes.
Well, that would just imply that you would disable the redirect behavior, because you would not want to try to go around the proxy server.
No, or the proxy server should also be exposing itself somehow into this. No.
Well,
But
so
it's a hypothetical question for now, at least.
Yeah, because it's a multi-threaded thing on the client side, but the server is actually going to see multiple connection requests. You would also want to make sure that the you might want to pin client IPs to a particular server for the duration of that moment, so that they are still talking to the same machine.
Yeah, and if you're using iPut, you're going to connect to the proxy server, and then basically it's going to redirect to the resource server that owns the storage, unless you've somehow worked your way around that. So this would behave in a similar fashion unless you disabled the redirect behavior on the client side in the Python client library, at which point all connections will be routed through the proxy.
Yeah.
So if you're using that proxy to round robin, catalog service consumers, for instance, it's really a question of how you set up the storage to accept those writes then at that point.
It's basically currently more a failover scenario, so it's rather static at the moment.
Okay, so the current behavior is the PRC asks iRODS, where's the storage and who owns that storage, so I can connect to that server.
Yeah.
And then it tries to open connections to that server. If the server is coming back, effectively with the, HA, the answer is I'm actually the proxy server, then everything should work just fine.
Yeah, that's now I understand it. But it's just more a remark, not really a deeper question, and definitely not a concern.
Very good.
Very good. Thank you.
Thank you.
All right. Well, Dan, everybody's clapping for you in the chat, so good job. virtual clapping. Thank you, everybody, and we'll do it again in a couple more months.
Yeah, looking forward to it. Thank you.
Thanks, Dan.
Sounds good. Thanks so much.
Bye-bye.
Bye.
Bye.